Hello again. In this segment, we're going to be building on our discussion of angular momentum and angular inertia to discuss another aspect of the shape of real objects, namely that the mass of objects is usually not distributed uniformly in space. Now, if we look at our demonstration, we built this little device in a previous segment. What we did here, just to remind us, is that we built a little complex shape, and we calculated the center of gravity based upon the intersection of two lines that divide mass equally across the line. And this is an equilibrium situation. No matter which angle it hangs, the mass on this side of an imaginary vertical line is equal to the mass on the other side of that imaginary vertical line. Now, it's not hard to imagine what will happen if we displace that somehow. If we put a mass, if we unbalance that, it's going to change. And we got to get this thread out of the way so that it can come into a new equilibrium there. The mass has now changed, and this didn't happen by magic. I didn't do it. What happened was the gravity pulled down on one side that was now heavier than the other. In short, in the phraseology of our previous segment on angular momentum, we've implied a torque force that helped to rotate this object about its center of mass. Now, in this case, it comes to equilibrium, but there are instances where this can be made to continue to rotate, especially if it's being driven by some kind of an engine or something like that. And in order to be able to understand that, we need to understand how the mass is distributed. Now, in this case right here, the mass is distributed uniformly because it is an object of uniform thickness. Let's now go to a more ideal representation. Let's come along and take a look at what our flat object would look like in cross-section. And so that's going to be something of uniform thickness. It's going to be looking something like this. The thickness is exaggerated with respect to our index card, but we could easily make it thicker to form something like a flywheel. And there's going to be an axis that corresponds to the center of mass that runs right through the middle of it, and this object will rotate about the center, that axis of the center of mass. And because the thickness of this is uniform, this means that the distribution of mass within this object is uniform. Therefore, that's going to have a certain degree of angular momentum to it. Suppose now, though, we take a different kind of object, we make it a bit more complicated. Suppose we locate most of the mass to the periphery and only a tiny bit to the center. So that now our object looks something like that, with, again, these two sides being symmetrical, more symmetrical than I'm drawing them. This object, too, will have an axis that corresponds to the center of mass. And just as in the case of this object over here, this object can be set in rotational motion by just turning the object around this axis right here. Now, in both instances, the distribution of mass in this is very, very different. Here, the mass is distributed uniformly through the object. Here, most of the mass is concentrated at the edges. At the edges, when this is set in motion, this large mass out here will be larger than this mass over here would be. Let's turn this up on its side. This is going to be a large spherical object. This is also going to be, disc-shaped object, I beg your pardon. This is also going to be a large disc-shaped object, but now we have an area that's quite massive where most of the mass is concentrated out here. When this is set in rotational motion, this will have a certain velocity, this will have a certain velocity, this will have a certain velocity, and that means that this kinetic energy will be proportional to the rate at which it changes position. This is a fancy concept called the angular velocity. And when we talk about the kinetic energy that can be stored in this, the kinetic energy is going to be some product of the angular velocity and the mass, just as it is in simple translational motion. If you spin this object at the same velocity, same angular velocity, now most of the mass is out here, traveling at a faster velocity than inside, but what's inside then is much less mass. And so consequently, the kinetic energy will be concentrated in this part over here in a way that it is not concentrated on the edge over here. That concept is embedded, or can be quantified, by a number that we can calculate called the first moment of inertia. And when we talk about moments in physics, we're not talking about instances in time. What we're talking about is objects that are related to the momentum of an object. So that's where that term comes from. Now, what we can do to calculate the first moment of inertia, again, there's some complicated calculations that you can do to be able to calculate it, but we can easily describe it just so you get a feel for what's going on. Suppose we take our disc-shaped object right here, and we calculate how much mass is going to be in this part right here. And then we draw another imaginary line, and we calculate how much mass is going to be in this part over here. Let's draw them in with colors. This is our first mass right here. The green is our second mass over here. The difference of mass between here and here is what we might call the delta M, or the change of mass. That change of mass corresponds to a change of radius. Here, the center of radius is at the center, and here, the radius is there, and the difference of radius is the difference between this imaginary radius and this imaginary radius right there. If we take all of those and we add them up, then we're going to get a total sum that's going to be proportional to the distribution of mass within the object. It's a very simple formula. The first moment of inertia is usually symbolized as an I, and that can be calculated by simply summing up, and there's a Greek letter sigma that is often used to signify that, all the increments of the mass, the radius squared, multiplied by the change of mass that corresponds with that radius. And so if we do this a number of times all the way out to the very edge, and we add up all the differences of mass times the square, the radius that is accompanying that change of mass, then you're going to get a total quantity, and that total quantity is the first moment of inertia. Now let's formulate a couple of hypothetical examples for how that might work. If we plot over here on this axis the square of the radius times the delta n, and we look at this over the radius, what we will find is that the first square radius times mass is going to be small. Why? Because the radius is small, and also the mass enclosed in there is small as well. And what we'll find is that those will start to accumulate as we go to the outer part of the object, and that's going to accumulate to the total moment of inertia, first moment of inertia of that disk. Let's just put in an imaginary curve that helps us keep track of that. That's going to be the way that the inertia changes in a flat disk. Now let's come back to our objects where the mass is distributed differently. In this case, the moment of inertia as you go out is going to be very, very small. It's going to be kept quite small because A, there's very little mass there. We've distributed most of the mass to the outside. And so if we come along and we draw in how the moments of inertia can be added up in our disk with the big edge over it, then it's going to look something like this. And because we get out to the edge before we actually encounter any mass, the radius squared makes this quite large compared to the effect of having the mass distributed uniformly. As a consequence, this curve right here, the curve for the disk with the big mass on the outside as opposed to the curve with the evenly distributed mass, those are going to have different moments of area. Different moments of inertia. If we come back to our diagram right here, the moment of inertia, first moment of inertia of our flat disk might be here. We can actually come up with a number, but we can illustrate what we need without the number. Whereas the first moment of inertia of this object right here will be located more out to the edge. Okay? And so the first moment of inertia is a useful tool to be able to understand how angular forces that impart angular momentum to objects actually does set them into rotation. Let's illustrate an example. If you take our flat disk, and if you take our disk with the mass distributed mostly to the outside, the first moment of inertia, let's put in our centers of gravity first. Here's our center of mass. The first moment of inertia of this disk right here can be thought of as an imaginary circle that contains all the distributed mass of this object. So now we have two things that describe the distribution of mass. We have the center of mass, which is in the middle of the centroid, and we have this imaginary circle right here in which all the mass is concentrated for the purposes of angular momentum. In the case of our flat disk, it's going to be here. In the case of our disk with the mass on the outside, it's going to be out there. The moment arm, in other words, for this object is going to be greater than the moment arm for that object. Now, when you have an object set into rotational motion, keep in mind that we said that the translational motion is going to depend upon forces acting through the center of mass. The degree of rotational motion is going to depend upon forces, tangential forces, acting with respect to this imaginary line which is given to us by the first moment of inertia. When this object is set in motion, a certain angular velocity, all its mass being concentrated here, all the kinetic energy of that motion will be concentrated in that disk right there. On the other hand, when you have the first moment of inertia out here with the longer moment arm, this means that the kinetic energy will be incorporated out here. Now there are two things to keep in mind. One is that if you have a constant angular velocity of these two, the angular velocity of the center of rotational mass here is going to be going at a slower velocity than the rotational motion of this large inertial mass here. Now, as a consequence, depending upon the distribution of mass, which is embodied in the first moment of inertia, depending upon that, a given rate of angular momentum will translate into different amounts of kinetic energy. And there's a nice formula for that, for the kinetic energy. Let's just compare our formula for the so-called translational kinetic energy. That is the kinetic energy when you set a body in motion. That's embodied in the center of mass. That's equal to the familiar equation that we've put up before, which is 1/2 mass times velocity squared. And velocity, of course, is the translational motion of the center of mass. However, you can also calculate a rotational kinetic energy, and this is important in understanding how things like flywheels store energy and those sorts of green technologies, the rotational kinetic energy is equal to the first moment of inertia times the angular velocity of rotation of this object. And that is usually symbolized as a Greek lowercase omega. It looks like a W, but it's rounder than a W. And the product of the first moment of inertia times the angular velocity will give you the rotational kinetic energy. Now it follows from this that the first moment of inertia of this disk, which is smaller than the first moment of inertia of this disk will store more kinetic energy for a given angular velocity, rotational velocity, than will this disk. And as I said, this is important in design of flywheels and things like that. But as we'll see in another segment, it's important for understanding an interesting adaptation that local maple trees have for enabling the dispersion of their seeds. Okay, well that's all for now, and we'll see you another time.